Okay, so now we have another problem. So it's electrodynamics exercise. This is actually a finite cylinder. Um, Finite cylinder with a potential on its side. Okay, that's the problem that we are trying to solve. So I will sketch the problem first. Here's a cylinder, okay? Okay, and we take that to be the z-axis. And that's x and y. Okay, let's take it like this. And that's 0, that's 0. And on the side, we're going to have a potential, okay, which depends on phi and z. Okay, so those other parameters, of course, are we need the height, and we're going to need the radius of the cylinder. Okay, so v phi z, that's given. Okay, now, in this case, the Laplace, okay, so I'm going to write the Laplace as partial rho phi z, so the second derivative, plus 1 over rho phi z plus 1 over rho squared phi z delta phi squared plus the second derivative with respect to z, that's equal to 0. Okay, so that's the full Laplace. Okay, and we need, there's dependence in every direction here. Okay, well, there doesn't seem to be dependence in the phi that, well, actually there's dependence because of this potential. Okay, so basically, first we do the usual Laplace ansatz, okay, the separation of variables, whereby we take phi rho phi z, and we end up with three functions. Well, sorry, not we end up with, we take this as the form of our solution. Okay, so we take this as the form of our solution. If we do the substitution into the Laplace and we divide by the solution itself in this form, we can write that what we're going to get is 1 over p delta squared p delta rho squared plus 1 over rho p delta rho. And then I will have plus 1 over rho squared, 1 over f partial phi squared, plus partial z partial z squared equals 0. Okay, so this is actually my new Laplace equation. Okay, and we can, of course, sorry, this has a 1 over z in front of it, okay? And we can think about how to satisfy these terms separately, mainly first by looking at the boundary conditions. Okay, so let's actually, the boundary conditions were given, but let me actually write, let me actually write them here separately. Okay, so we're going to have a boundary condition whereby phi rho phi at h is equal to phi rho phi at 0, and that's equal to 0. Because that's one boundary condition, the top of the cylinder, the disk at the top and the disk at the bottom. And we're also going to have phi r phi z, and that's equal to v phi z. Okay, so these are the boundary conditions. V phi z is some given function. Okay, so that's but first of all, sorry, I need this slide once more. this boundary condition is actually easily satisfied if we take z of z to be sine m pi over h times z. Okay, so that's and in this case, well, this becomes minus m pi over h squared. This whole term. So this whole term is going to be replaced by minus m pi over h squared. Okay. Then the other thing is that, well, we have to do something with f phi. Okay, and we're going to take f phi to be e to the I nu times phi, because what we know about this is that we are working in a cylinder, okay, and this obeys the rotational symmetry of the cylinder, okay. So basically, and that actually makes um, this term is going to become minus nu squared over rho squared if we do that. Okay, so basically what we're going to be left with is an equation for this function that I've been calling p plus 1 over rho partial p partial rho. And this is going to be minus nu squared over rho squared plus m pi over h squared. And we can multiply it by p, and that's equal to 0. Okay, so that's the equation that we're going to have to work on now, okay? And what we first do, again, is to apply a variable transformation of the form k rho, but k, we're going to choose k, or kappa actually, the way I've written it, as m pi over h. Okay, and then so what's going to happen then is well, so a derivative with respect to rho is d d rho. So that's actually kappa d dx. Similarly, you can replace d rho, the second derivative, with kappa squared d dx squared. Okay, so so basically what we're going to get is the following equation for p. D squared p dx squared, once we make all these replacements, 1 over x dp dx minus nu squared over x squared plus 1 p equals 0. Okay? So that's actually the second order differential equation that we're going to be after. And it turns out that this is actually a known equation, and the relatively its solutions are well known. Okay, this is actually it leads to Bessel functions. These Bessel functions are actually the Bessel functions of imaginary argument. They're known as the Bessel functions of imaginary argument. Okay, so let's see what is meant by this. So I'm going to take the ansatz again as m equals 0 to infinity, am x alpha plus m. Then I have p prime x is equal to m is equals 0 to infinity, am alpha plus m x alpha plus m minus 1. Okay, and then I'm going to need to divide that by x because I'm really after this, so this 1 becomes a 2. And then I have also p prime of x, which is m equals 0 to infinity, am alpha plus m minus 1. And again, I have x, well, it's not going to fit, but alpha plus m minus 2. Okay, so that's what I have. Okay, so basically my equation, when I substitute here, can be rewritten. So I'm going to sum these up. That's easy. So these first two terms are going to give me m equals 0 to infinity, am alpha plus m squared, x alpha plus m minus 2. Okay, and then this term will give me minus nu squared, m equals 0 to infinity, am x alpha plus m minus 2. And I'm going to take this on the other side of the equation. So after this equation, this equal sign, I'm going to have m equals 0 to infinity, am, and it's just 1 times the solution itself, the power series itself. Okay, so that's the starting point to actually work out what this power series means. And one thing that we can immediately say about the power series is that for m equals 0, I have x to the alpha plus m on this side. That's where it starts. And then I'm going, x to the alpha rather. Okay, then I'm going to have x to the alpha plus 2, x to the alpha plus 4, and so forth. Okay, on this side, however, I'm going to start at alpha minus 2. So these alpha minus 2 terms on this side do not have a matching term on this side. So I can actually say alpha plus m, where I'm going to take m to be 0, squared minus nu squared is, I'm going to take that to be equal to 0. So I can take alpha as plus or minus nu, and that way I have a sensible solution for this equation in for the power series. Okay, so then I'm going to shift the indices on the left side. So I'm going to have m equals 0 to infinity, m plus 2, alpha plus m plus 2 squared, x alpha plus m. Okay, well, actually, I could have made this a nu, so yeah, that's what I should do, minus nu squared, m equals 0 to infinity, m plus 2, x alpha plus m, okay, and that's equal to m equals 0 to infinity, am x alpha plus m. Okay, so basically from this equation we can read the recursion relation. Okay, so am plus 2 is going to equal am divided by nu plus m plus 2 squared minus nu squared. Okay, and while we can do something with this to make it simpler, am plus 2 is equal to am divided by, what is this going to be? So if I extend this, I'm going to have 2 nu m plus 2 plus m plus 2 squared. Okay, so am plus 2 is equal to am divided by 2 nu plus m plus 2 times m plus 2. Okay, so that's actually one way of writing the recursion relation, but I actually prefer to reindex this. Okay, so I'm going to say that I'm going to replace m with 2j. Okay, I'm going to slightly shift the indices around. So I'm going to, instead of 2j plus 2, I'm going to write j plus 1. So I'm going to write aj plus 1, and that's equal to, well, since I divided the indices by 2, that's going to be aj, and that's divided by what? 2n plus 2j plus 2, but that's actually 2 times nu plus j plus 1, sure, and this is actually 2 times j plus 1, okay, which I can write simpler yet as aj divided by 4 nu plus j plus 1, j plus 1. Okay, and now I'm in a position to attack the whole series, because, for example, I can say that, well, what is a1 in terms of a0? Okay, well, that's easy, right? So nu 4 nu plus 1 nu plus 1 times 1. Okay, and then what is a2 in terms of a1? Well, that's 4 nu plus plus 2 actually, and times 2. Okay, but then I can immediately substitute this. I have a0 divided by 4 squared, and here I'm going to have nu plus 2, nu plus 1, and times 2, 2 times 1. So I can say in general that aj is equal to a0 divided by 2 to the 2j, nu plus j factorial, nu factorial. Okay, so this actually, I can, that's actually my coefficient. And for example, I could take a0 to be 1. I'm not sure if that's the convention, but for now, okay, for this solution, that's my my modified Bessel function. So let me actually write the solution of this modified Bessel function, okay, because that's important. So the modified Bessel function, which I'm going to call I nu of x, is, that's an equal sign, is, well, x to the nu, and then I'm going to sum j equals 0 to infinity. And well, it's actually, if I take a0 to be 1, well, what this ends up being is x to the 2j nu factorial divided by 2 to the 2j, j plus nu factorial, j factorial. Okay? Yeah, okay, so that's that. Yeah, okay, so actually, but I don't remember the convention. Okay, so maybe this new factorial is canceled, because you can in principle take a0 to be 1 over nu factorial, and then you wouldn't have this nu factorial here. I seem to recall that that's probably the convention. So let's rewrite that. It doesn't really matter for our solution, as you will see. Okay, so x to the 2j divided by 2 to the 2j, j plus nu factorial, j factorial, I nu x. Okay, so that's let's take this to be the definition of our Bessel function. Okay, so now we're home, okay, and now we actually go back and we can build up our entire solution, okay. So what did we say? Okay, so what did we say? This was our problem. Okay, so that was our problem. But what we said, I'm looking for the relevance slide that I wrote here. But no matter, I probably just have to rewrite what the things that we said. We said that phi rho phi z is going to be a product. Okay, so I'm going to write well, first of all, it's going to be I nu, and we actually wrote m pi rho divided by the radius. Okay, so it's going to be a modified Bessel function. Then it's going to be sine m pi z over h. Okay, and then here we're going to place a m nu cosine m phi, no, nu phi, sorry, nu phi plus b m nu sine nu phi. Okay, so that's going to be our ansatz solution. Okay, and this has to be summed over m nu. Okay, so this is actually the full solution. Okay, so that's the only thing is that one has to, of course, determine the coefficients a m nu and sine b m nu by inverting two sets of Fourier series here. Okay, so that's actually, so the next step I would just outline it because we have it here in a general sense. Okay, so what we know is that on the boundary, on the side actually, this is V0 phi z. Okay, or v phi z. It wasn't v0, doesn't matter. Okay, so, but it's a known function. Okay, so that's the important part. It's a known function. So how do we deal with that? Okay, so what we know is that this known function, okay, is going to be given by m nu I nu m pi. Actually, sorry, I made a mistake because this should have been an m pi over h, not an m pi over r. Okay, so let me actually just prove that to you. Remember that the kappa, so remember the kappa was actually m pi over h. Okay, but I don't seem to be able to recover that slide. But yeah. Okay, but anyway, the important thing is that, yeah, this is an m pi over h, not an m pi over r. Sorry, that was a mistake. Okay, so this is our ansatz solution. And so our next step, m pi over h r, because I substitute r, rho equals r, and I'm going to have here sine m pi z over h, okay, and a m nu cosine nu phi plus b m nu sine nu phi. Okay, what we need to do now is to determine these coefficients. Okay, the first thing we're going to do is to integrate both sides of this equation against some cosine function. Okay, so what's that going to give us? Well, on the left side, it just gives us 0 to pi v phi z, okay, cosine nu prime phi d phi. So that's what it gives on the left side. On the right side, well, it's going to actually, first of all, with the sine, it gives 0, but with the cosine, if nu and nu prime are equal, it gives the contribution. So I'm still going to be left with the sum m, I nu m pi r over h. And then I have here sine m pi z over h. And then I am going to have my a m nu. And this cosine, when nu is equal to, sorry, this should be a nu prime. So that actually gives us a pi, okay? Because what I did is actually to get that pi was 0 to 2 pi cosine squared nu prime phi d phi. That's equal to pi. Okay, so that's one. And the second thing we have to do, of course, is to integrate this against another sine function. Okay, so where are we now? Right now we are at 0 to 2 pi v phi z cosine nu phi d phi, and that's equal to the sum. The sum actually runs from this, the sum actually runs from 1 through infinity, okay? I never wrote that, so what? I nu m pi r over h sine m pi z over h. Okay, and I have here a m nu pi. Okay, so the next step is to actually extract something out of this sum. So it's actually, and of course, m, here's a running variable z. There's no running variable here. So r and h are all fixed, and m and pi, m is a running variable, I guess. But what we need to do here is to integrate from 0 to h dz sine m prime pi z over h on both sides. Okay, so on the left side, we're going to have 0 to h, 0 to 2 pi v phi z, cosine nu phi. Yeah, I guess I can write a d phi here. And then I will write sine m prime pi z over h dz. Okay, and on this side, I'm going to have I nu m prime pi r over h, a m nu times pi, and this is actually from 0 to h, so actually it's going to give me an h divided by 2. Okay, so if in general, depending on what this function is, if you are able to carry out these integrals, then you have a closed solution because you have an equation for the coefficient a m nu, and of course, if you want the coefficient b m nu, that just means that this here gets replaced by a sign. Okay, so this is actually the full solution strategy for these types of problems. Let me actually make a few other remarks here. So basically, um, we had the function I nu x, which is x to the nu, j equals 0 to infinity, x to the 2j divided by 2 to the 2j nu plus j factorial j factorial. That's what it was. So an important part, so that's actually the modified Bessel function. It's related to the usual Bessel function. You can, there's actually a relation in which what you have to do actually is to replace x by an imaginary number. Okay, so it is assumed that the original Bessel function, the j nu x, uh, um, takes a real argument, okay, but if you make x ix, then you actually get this one. And the important difference actually is, remember that in the usual Bessel function, you have a minus 1 to the j here, so these terms alternate in sign. Okay, and that's why on the real axis, the usual Bessel function has zeros, whereas this just grows on the real axis. Okay, and because of that, we don't have on the real axis we don't have an orthogonality relation, but we didn't need one. Recall that this function is just here. Okay, so if it has some value, we have to figure out what that value is for. Sorry, this is an m prime. Apologies. I guess. Okay, so we have to figure out what this value is, but we have the formula to figure it out in principle, so we can that we should be able to do. Okay. Thank you very much.